Hello all. This is just a quick lecture on the stuff we covered on September 8th and 9th. So if you were absent or if you would like a refresher because you didn't get something in class, or maybe you just want to make sure that you understood everything correctly, this lecture is for you. All right, so the very first thing I want to go over is a little bit is atomic structure. You will notice that in your page for September 8th and 9th, you actually have build an atom activity. It looks like this. So I'm going to go ahead and build an atom. And the atoms I'm mostly interested in are lithium and beryllium, but I'm going to start from hydrogen and then build my way up. Just to refresh what it is atom is made of. Because that's actually kind of important in our class. Not too important, but important in order to understand like what electricity really is. So atom usually consists of two parts. It has a nucleus and it has an electron cloud. So nucleus is typically made of protons and neutrons. So right now I have a proton and I have just one, so I don't need any neutrons. And you can see that when I have just the proton, I have a positive ion. Now, if I add an electron to this, my atom all of a sudden becomes neutral because my positive and negative cancel each other out. Now, if I add another electron, it no longer cancels out. I now have two electrons and one proton, so it becomes a negatively charged ion. So what if I add another proton? Well, it doesn't look like anything is happening right now, but if I check stability right here, you can see that it starts shaking. Basically, protons are fighting inside the atom because they're both positive and they repel each other. So think of this as a fight, and we need to get some in between them so that they don't kill each other, and that someone is neutron. So we put a neutron, immediately it becomes stable. Once again, now I have a completely different element. It's helium. The element is generally determined by how many protons you have. So now this is a new element. It's called helium. It's a noble gas. If I take away electron, once again, I'm going to have a positively charged ion because I now have two protons and only one electron. If I put it back, it's neutral. If I give it another electron, once again, it becomes negatively charged ion. All right, so it seems like the charge of our ion depends on the balance of our protons and electrons. So next one, I'm going to add another proton. Once again, it becomes unstable. So I need to add another neutron. This is the real three-way fight. So we have to break that up. Here's one, here's two, and that's enough. Excellent. So you can see that this is a lithium, and this is one of the metals I originally told you I'm interested in. And the reason I'm interested in metals and lithium in particular, they have this outer electron, and it's all by itself. Now, normally, your second orbital, your third orbital can have up to 8 electrons, and anything over here, your fourth and fifth, can have up to 18, okay? So 18 electrons is a lot, but the nice thing about metals is that they all, no matter if it's a copper, if it's iron, if it's vanadium, they all have one electron or two electrons in the outer shell. And that property that they have one electron or two electrons in the outer shell is what makes them a good conductor. And I will explain that in a couple of minutes. So once again, if I take away this electron, I have a positive charge. If I put it back in, I have neutral atom. And if I add an electron, I'm going to have a negatively charged ion. And the last but not least, I wanted to build a beryllium. This is another metal. I'm going to add some more protons to make it stable. And you can see this one has 2 in the outer orbital. Now, anything beyond 2, I'm really not that interested in, with the exception of aluminum, possibly, and some of the other ones that are further down. But as far as the second row, I'm not really interested in anything beyond 2 because the rest of them are simply put non-conductive. Now here's what's happening when you have 1 or 2 electrons in the outer orbital. The attraction between the electrons and the nucleus gets weaker and weaker the farther out your orbital is going to be. So if you have like a 4th orbital somewhere over here and you have just 1 electron out there, the attraction between it and the nucleus is very weak. It's kind of like having a girlfriend in Dallas. You're kind of in relationship, but not really, right? This is the same thing. The attraction is very weak, and it doesn't take a lot of energy to give that electron a little push and get it moving somewhere else. And that, of course, is what happens when we have an electric current. So let's write down some definitions. I'm going to go ahead and write down some definitions for us. So the first definition we need is charge. And we came up with a whole bunch of different definitions in all of my classes. The one that I like the best kind of combines them all. And this is the definition I'm going to give you. It's the amount of electrons in relation to protons the object has. Okay. Now, why did I write in relation to protons? Because literally we are looking, does it have the same number of electrons as the proton does? Does it have different number of electrons? We have to take a good look at that and make sure it's all what we want. Okay. So this is basically our functional definition of charge. Now, here's another thing. Why did I say the object? The reason I said object is because when electricity was discovered, people had no clue what atomic structure is. What they did know, however, was things like static electricity, when you can rub your hair on the balloon and then your hair sticks to the balloon. Now, what really happens in that particular situation is that you literally rub enough electrons off your hair onto the balloon. Okay, so now I'm going to move on. The second definition we need is what is electric current. And if you think about the current, the very first thing that comes up to you is something like a river. In fact, we can go ahead and Google that, and you will see that if I put in current here, I'm going to upload images. You can see electric current and you can see water, right? You can see water. You can see river. You can see ocean. You can see air currents. You can see all sorts of currents. Of course, the ones that we are interested in is electric current. Now, just like in a river, it's water molecules that move in the current. In our class, it's electrons or charges that move through the object, through our conductor. So the definition of the current is a flow of charge. And I'm going to put electrons in the parentheses because in our class, it's almost always electrons. Keep in mind, ions can also flow when you have a solution of some sort where you have one substance dissolved in the other, and that substance ionizes, as in it goes separate ways, and it has positively charged and negatively charged ions floating in it. For example, if you make salty water, that will definitely conduct electricity, but it will be ions. We saw them, right? The positive ion, negative ion, right? Sodium, things like that, they will be flowing in the current, not electrons themselves. But in our class, it's almost always electrons because we care about a current not inside a solution, but inside a copper or iron wire. And over there, it's always electrons. Now, here's the thing, guys. Electrons, you saw them. They are actually tied to their atom. They are tied to their atom, and they're supposed to stay in those orbitals. They're not supposed to go anywhere from them. So how come we actually have a current? It's like I mentioned before, in order to get them flowing, you have to give them a push. And depending on how much push you need, that determines whether your material is conductive or not. Some materials like fluorine or noble gases, things like that, silicon also, no matter how much push you give it, you will have no current whatsoever. And we call that insulator. And metals, of course, conductors because we don't have to push them a lot. So that push's got to have a name, and we generally speaking call that voltage. And I'm going to give you a very improper definition of voltage in terms of physics, but it's a very much working definition. It really what voltage is and what it does, okay? So voltage is a force that makes electrons, or charge, if you will, flow, okay? Without voltage, electrons are not going anywhere. They're not going to go. They're not going to flow. They're just going to sit there around the atom. So one good analogy that I like to bring up in this particular case is a hedgehog. This guy. See? Adorable. Well, the analogy goes like this. A hedgehog is a very proud bird. Yeah, that's a bird. Because it's not going to fly unless you kick it. So same with electrons. Electrons are not going anywhere unless you actually make them go. So the next thing we need to talk about is what is current and what is voltage measured in. But before we do that, we actually have to figure out what are electrons measured, what is charge measured in. And the problem with that is that all of this stuff was discovered in the end of 18th century, beginning of 19th century. And that's when people had no idea what atomic structure is. So that's the guy who discovered charge. His name's Coulomb, and he's French. He kind of looks French too. And you can literally see that it says electric charge, current, charge, all sorts of things, right? So he worked with all of those things. And they named the unit of charge. They named the unit of charge after him. And the unit of charge is called Coulomb. Now the problem with coulombs is that it's a very large and cumbersome unit. As far as units that do not make a lot of sense, this one really takes the cake. And this is the symbol. It's capital C because it's the guy's name. And this is how you actually say coulombs, because you know you spell it completely differently. This is how you pronounce it, coulombs. Okay, coulombs. Okay. So if the current is the flow of charge, then we gotta have coulombs in there, right? And flow generally means how fast. So the way we do it, we literally set up a checkpoint in one point in the wire, and we see how many coulombs of charge float past that point in a single second. So that would be 1 amp. Units of current, or amps, or ampere, right? And I usually call it amp, so do most people. Ampere is another French guy. So this is Coulomb per second. And I really need to stop misspelling things today. So this is coulomb per second. Let me do it like this. There, that's much better. This is coulombs per second. So we usually write it C over S, right? And you know, since we're pretty lazy lot, we tend to say that just say 1 amp instead of coulomb per second because that takes time. And the last but not least unit that we need to have is, of course, the units of voltage. And that is pretty self-explanatory. I mean, voltage, volt, right, makes sense. They would be the same. So units of voltage is R volts. And I'm going to go into greater detail this coming week, what volts really are. Because right now we only know what it does, but we don't know why it does what it does. We're going to talk about it some more this coming week. But this is really all we went over last Tuesday and Friday. So this is your refresher, or if you were not there, this is the lecture. So I hope that was helpful.